Yeah, it might be two elements put together. It might be one element put together multiple times, right? Examples of compounds are things like NaCl, CO2, H2O, right? Those are all examples of compounds. They are they're chemically bonded together. So one or more atoms are chemically bonded together. And so we're gonna learn how to name the chemical compound. Name the chemical compound based on different properties and rules. Do we know the names of any of these up here on the board? Water. Okay, that's water. That's more of a nickname, but okay. Carbon dioxide. This is carbon dioxide. That follows a pattern of rules that we're going to talk about in a little bit. It has a prefix. It ends in "ide." We're going to talk about that. What's the other one? Salt. It is salt, but it's more of a nickname. Do you know what the actual chemical formula is? Sodium chloride. This is called sodium chloride, but it is table salt. You're right. Okay, it is called sodium chloride. And so we're going to figure out how do we come up with the formal name for all of these different compounds. Okay, we're going to come up with formal names for all of our compounds. And there are three different categories of naming that we're going to cover in this chapter, but we're going to start with something called ionic formulas. Okay? Ionic formulas or ionic naming. Ionic means that it is a chemical compound that is between a metal and a non-metal. Highlight that, circle it, do whatever you need to, but we need to know that it is between a metal and a non-metal. Okay, so I want you to actually take out your periodic table right now. I want you to take out your periodic table and look at what section of the periodic table are the metals. At the left side or the right side? All the metals. Left side or the right side? Left side or right side? The left side. Do you see on your periodic table where you shaded all those things in or you separated them? Yes or no? Yes, ma'am. The left side of the periodic table, yeah. Metal, yeah, this is, sorry, a little and symbol. Say it again.
Majority of this whole thing is metals?
Yeah, most of the whole periodic table is metals. And when I say left side of the periodic table, I mean left of that stair step line that we drew in. Remember this stair step right here? This gives us a hard separation between metals and non-metals, okay? So anything to the left of that stair step line is a metal. So I want you to flip over your periodic table now to something called the periodic table of ions. We haven't really looked at that yet before. Periodic table of ions, okay? What do all of the metals, what type of a charge do all of the metals have? Positive. They all have a positive charge, right? Do you see all those metals? They have a positive charge. What charge do the non-metals have?
Negative.
A negative charge. Okay, so when I say periodic table of ions, what does an ion mean? Let's think back to our last couple chapter here. What does an ion mean?
Charge.
An ion is any charge, an atom that has any type of charge. So if we're talking about an ionic formula is between a metal and a non-metal, another way we could say that is between a cation, which is a metal, and an anion, right? Non-metals have a negative charge, right? This is negative, and this is positive. So another way to think about an ionic compound is that it is built between a positively charged ion and a negatively charged ion. Okay, that's where we put them together. So does this NaCl, does that fall into that category of an ionic compound? Is sodium a metal and chloride a non-metal? Why don't you check your periodic table?
Pardon me?
Check your periodic table. Does sodium chloride fall into the category of an ionic compound?
Sodium is yes.
Yeah, sodium is a metal and chlorine is a non-metal. So that falls into a category. This is an ionic compound. What about CO2? Is it an ionic compound? No, because those are both non-metals. So we'll learn about those later. What about H2O? Is it a metal or a non-metal? Is it ionic or not? It's not ionic, right? Because hydrogen and oxygen are both non-metals. So we'll talk about those two later. But NaCl is going to fall into our category of ionic compounds. Okay, so we know how to identify an ionic compound. It has to have a metal and a nonmetal. So now let's kind of go over some rules about how we can name them, okay? I want you to take a look at your periodic table of ions, and let's answer a few questions here first. I want you to look at your periodic table and see if we see any patterns of the charges. Okay, all the elements in group 1 right here, what is their charge?
Positive 2.
No.
Positive 3.
Positive 1.
Was positive.
It says positive, but we assume there's a 1, right? So when it just says plus, it means plus 1.
Plus 1 each column.
And then what's the charge of the group 2 elements?
Positive 2.
Plus 2. We skip these guys because they don't follow all of the rules. Then we come over to this group right here. What's their charge?
3.
Plus 3. What happens here?
There's only certain.
Yeah, they don't all have a charge listed, do they? What about this one?
Negative 3.
Negative 3.
And plus 3.
Negative 2.
Negative 2.
Negative 1.
Negative 1. Do we see the pattern that happens there?
And then
If you work
local
from the
gas.
If you work from the outside, you can start with plus 1 minus 1, plus 2 minus 2, plus 3 minus 3. But what's the one group that we exempt from that? Why don't we give noble gases a charge?
They're non-metals and they're not metals.
No. Why do the noble gases not have a charge?
Because they are gases.
They have complete orbitals. Okay, so let's talk first about how do the elements get their charge. I don't want to talk over today. I don't want to do it. Okay, so please listen. How does an element get its charge? Okay, let's answer that question first. How many valence electrons do the group 1 elements have?
1.
They're in group 1, so they have 1 electron in their outermost shell, right? We just did electron configuration. So rubidium's last electron is 5s1, right? Yes or no?
Yes, Mom.
Okay, so it has 1 electron in its outer shell. Does it want to gather in 7 more electrons, or does it want to just give away that 1 electron?
Yeah.
It wants to give away that 1 electron because underneath that, it would have a full shell. So when rubidium gives away that 1 electron, what charge does that leave it with?
Neutral.
Nope. If it starts with 37 electrons, that would be neutral. And it gives away its outer electron. Now it only has 36. It would leave it with a positive 1 charge. That's how that charge comes about. Strontium wants to give away its 2 outer electrons. So that has a plus 2 charge. That's where these charges come from. They're not just made up from nowhere. It's about how many electrons they want to give away or take in. If strontium has 38 electrons and its outer shell has 2 electrons in it, right? These are the S2 electrons. It doesn't want to bring in 6 more electrons. It just wants to get rid of those 2 because when it does, it will have a full shell underneath, right?
And that's what any number?
What do you mean any number?
Meaning like...
They give those electrons away. They're supposed to have 38, but they give 2 away, and now they have 36 electrons and 38 protons still. That leaves them with a plus 2 charge. Right? So that's how this charge came about. Let's flip to the other side and look like at fluorine. Okay, fluorine in its outermost shell has 7 electrons, right? It's in group 7, so it has 7 electrons. Would we agree? It's got S2 and it's got P5, so that adds up to 7, right? It's got 7 electrons in its outer shell. Does it want to give away all of its 7 to end up with a full shell, or does it want to bring in 1 more? Okay, so when it brings in another electron from something else, right, it was supposed to have 9, it has 9 protons, but now it has 10 electrons, which gives it a negative 1 charge. That's how the charges are assigned. I just go over that because I think it's important for you to know that the charges assigned to each atom, they're not like made up from nowhere, right? It has to do with their valence electrons and what they need to be comfortable, to be complete, right? To have what we consider a full octet. Does that kind of make sense? Okay, that's just a kind of an introduction to why the charges matter and what makes it, how it works. Okay, you're not going to necessarily have to be able to explain that system, but I want you to have a little bit of a background knowledge with that. Okay, so now let's get into the actual naming part of it. Bless you. Let's get into the naming part of it. Okay, I want you to take a look at your periodic table of ions. That's the side with all of the charges on it. And I want you to look at all of the cations. Take a look at all the cations. Did their names change? Take a look at the name for calcium and potassium and chromium. Did any of their names change?
No.
So cations keep their name. But what's different about the anions? Do they keep their regular name?
No.
What's different about them?
You had I to the end.
Right. They change their ending to end in IDE. They have a suffix. Right? They change their ending. It's not phosphorus anymore. It's phosphide. Phosphide, right? Do you see how that's written on your periodic table of ions? I want you to look at that and be able to see that difference there. Okay? Look over here at phosphorus. So when we see the word phosphide, we know that we're not talking about a neutral phosphorus atom. We know that we're talking about P with a -3 charge. That's the difference. Okay? The problem is when we talk about ions that are positive, we actually don't know if they have a charge or not based on their name because their name doesn't change. So that's a little trickier. Okay? But anytime we see an IDE, we know that we're dealing with the negative version of that particular element. Okay? So that's when their atoms are single. But let's get into it when they start to bond together. Okay? We're going to start with something called binary ionic compounds. Okay, these are the most simple compounds that we can name. Binary probably means it has how many atoms?
By 2.
2. Okay, so these are ionic compounds. These are ionic compounds with only 2 elements. Say they only have 2 elements. Okay? Here are some rules about binary ionic compounds. The compound itself, when you put these elements together, must be neutral. So what do we mean when we say neutral? What charge represents neutral? 0, right? It must have a 0 charge. That means we have to fit these atoms together in a ratio that gets us to a 0 charge. So we might need more than one of our elements to go with another one, right? Based on their charges. So they must be neutral. So that essentially means our positives and our negatives have to cancel each other out. Okay, so let's start with a simple one here. Let's say that we want to build a formula between magnesium and bromide. Magnesium and bromide. Let's say that we want to build a formula. We want to build a compound that has magnesium and bromide. So the very first thing we do is we come to our periodic table of ions and we find out what is the charge of each of those atoms.
One is neutral, one is negative, one is +2.
Okay, so let's look at magnesium's charge. We see up here that it has a 2+. Okay, I don't really like to write it 2+. I write it +2, but they mean the same thing. So magnesium is +2. And what is the charge for bromine? -1. So if I just fit those together, one magnesium and one bromine, does that give me a neutral charge?
No.
It doesn't, because +2 and -1 don't make 0, do they? So how can I fix that? Can I just put in half a magnesium atom? No, how can I fix it?
You put in 2 bromine.
I put in another bromine, which has a charge of -1. And so now that tells me +2 cancels out the -2. And so I build my formula to be Mg1Br2. You see how that comes together? I needed 2 bromines to cancel out the positive 2 charge of magnesium. Now, if there is a 1, do I have to write it? I don't. I don't need to write a 1. So I just am going to get rid of that. Okay, it's just MgBr2. And the name for that compound is very, very simple to name. All we're going to do is name the cation, then the anion. So the formal name for it is just magnesium bromide. That's it. Magnesium bromide. Yes, Anthony.
Why is it not?
Good question. In ionic compounds, we don't use prefixes at all. We use them for carbon dioxide, but that was not an ionic compound. Remember how we talked about that's 2 metals? So we don't use any prefixes with this set of naming. That's not the rules for that. So we'll do a different set of naming where we have to use prefixes. Yep. This one is just called magnesium bromide. Okay? Magnesium bromide. I had to have 2 bromides to be able to cancel out the positive 2 charge of magnesium. Okay? Calcium oxide is a... Yeah, so don't they just cancel?
So it's neutral?
It already is neutral, and so we don't leave our answer like this with charges. Our answer has to be no charges in our final answer. So our answer actually just comes down to be CaO. Right? Because don't they just fit together perfectly? Yes. 2 and 2? Okay, not so bad, right? You want to try another one? And remember, the written name for it is just the cation name and then the anion name. Okay, whenever we build ionic formulas, the cation always comes first. Always, always, always. Any chemical formula that we build is always built left to right on the periodic table. So whatever element comes first on the periodic table, farthest left, that's the one that's going to go first in our name.
So this is left to right?
Always left to right. Okay, we're going to build them always left to right. All right, let's try lithium phosphide. Lithium phosphide. Okay, I want to write it out. I need you to get into the habit of writing it out. So lithium has a +1 charge. And phosphide is a -3. How do I know that I'm working with a minus version of phosphorus?
Because
It ends in IDE, right? Okay, so the first question we ask ourselves is, does it go together perfectly?
No.
It doesn't go together perfectly, so I'm going to have to make some changes.
you don't talk to negatives.
I need 1 more lithium. That would, that would make it +2 over on the left, right? And if I add 1 more, now I can cancel. 3 plus and 3 minus gets us to neutral. So my formula is Li3P. Right? And how many phosphide do I need? Only 1, but I don't need to put the 1 there, right? I can leave that off.
It's by itself as well.
So aluminum is +3 and oxide is -2. So do we see a simple solution for how these are going to go together? It's not like a super simple solution, is it? Is there a way we can get there?
Yes.
So I need the charges to cancel out, right?
Add like a fluorine, right?
Okay, good. That's a good option, but I want to keep the compound between just aluminum and oxide. So how many of each of those do I need to put in to get my charges to 0? What do you think?
2 aluminum, 3 oxide.
Okay, so I want to basically find the least common multiple of my charges in this scenario, right? Least common multiple between 2 and 3 is 6, right? So if I put in another aluminum, oops,
Or
sorry.
you can just add 2 more oxides.
That's right. So then I can go another oxide, right? And so that gets me to a +6 and a -6 so that they
You
cancel.
have to put the -6 number.
Well, I'm not going to put any charges in my final formula, right? Final chemical formula gets no charges. I just know that I used 2 aluminums, and how many oxides did I use? 3, right? And so that's my final formula. It's so important that we don't include any charges in our final formula at all. None. No charges in our final formula. Okay? Tell me what questions we have so far. Okay, I'm going to show you an easier way. So we're going to keep this same example here. Now I'm going to show you kind of a quick shortcut method. Okay, and this is called, listen, I need you to stay with me here. This is called the crisscross method. So I want you to start with our beginning again. Aluminum is a +3 and oxide is a -2. We're going to do what we call the crisscross method. And that means we're going to ignore the pluses and the minuses. We're going to take those away. And we're going to crisscross the charge down to a subscript. And now it becomes Al2O3. And isn't that exactly what we had for our answer right here?
So you can work for any of them.
You can, it works every time. It works every time. Okay?
Interesting.
Every time. So let's go back and look at some of the ones we already did. If we start with Li and P, I'm going to get rid of the plus and minus, bring the 1 down, bring the 3 down. That leaves me with Li3P1, but we don't have to write the 1. Isn't that exactly what we came up with? Yeah. If we go back to our other one, what's the difference here? If we crisscross here, that would leave us with Ca2O2. That doesn't look the same as this one. That's right. So if that's the case, we would have to reduce these down back to CaO.
But if we write Ca2,
Ca2O2 is wrong. Yep. Ionic compounds have to be reduced. Have to be reduced. But you'll probably see that right away that they fit together perfectly. So you don't need to do the crisscross there. All right, go Raheem.
So if it's a C normally
+2. Nitride is -3. So the first question we ask ourselves is, does it fit together right away? And the answer is no, it doesn't, right? Because the 2 and a 3 don't cancel right away. So then I could go through the counting process, or I could just do crisscross. Okay, so if I'm going to crisscross, I get rid of the plus and minus. I bring the 2 down to nitrogen and the 3 down to beryllium, and I get Be3N2. And that is the chemical formula for beryllium nitride. Look at your periodic table of ions, and I want you to look up at this box up at the top right here. It says table of polyatomic ions. What do you think polyatomic means?
polyatomic.
Three atoms.
Yeah, poly means many or multiple. So multiple atoms that make an ion. And so you see all those polyatomic ions up there in the box? They all have very specific names, but they're a group of elements that have a charge. Right? That's what a polyatomic ion is, a group of elements that have a charge. And so these polyatomic ions, most of them have what type of a charge?
Negative.
Most of them have a negative charge. So we're going to treat them just like we treat the anions that we do regular. But the difference is that polyatomic ions always keep their name. Polyatomic ions keep their name. Okay? So a lot of these polyatomic ions end in ate or ite. Those get to keep their name. That's part of their identity, right? Chlorate. Let's go through a couple examples here. I want you to look into your box and find chlorate. Chlorate is ClO3 with a -1 charge, right? It just says minus, but we assume there's a 1 there. So -1 charge. Chlorite, it has a different ending. Chlorite is ClO2 with a -1 charge. And what would it be if I just said chloride?
It'll just be Cl -1.
It would just be Cl -1, right? Because chloride comes from the periodic table, the regular element, right, with its ending. So these are totally different substances, and they have different behaviors and different properties. So we need to understand when we see chlorate, we're telling ourselves that's ClO3 -1. They have different properties. So you'll always get to see this box. I'm not going to make you memorize any of these. You'll always get access to this. And so we just need to know if we see something that ends in like an ate or an ite, that's usually going to come out of the box. Okay, and we'll go find it there. So let's work with chlorate, and let's build a compound that has chlorate in it. Let's try potassium chlorate. Okay? The cation keeps its name. The polyatomic ion keeps its name. Potassium chlorate. All right, what is potassium's charge?
Plus
K plus what?
3.
Plus 1. And chlorate, we said, comes from our box. It's ClO3 minus 1. So do I need to bother doing the crisscross here?
No. Yes.
No.
I don't think so, right? I see that they go together perfectly. Plus 1 and a minus 1. So that means it would just be KClO3. This 3 is part of chlorate's identity. We never, ever, ever change that subscript. That is one that we will ever change because chlorate is ClO3 minus 1. Right? We don't ever change that 3. We won't ever reduce that 3 because it's part of chlorate's identity. So we don't change that. So our final formula is just KClO3. Do we see how that fits together? Cation and anion? Okay, let's try another one here. Let's try, bless you, aluminum nitrate.
Plus 3.
Aluminum nitrate. Okay?
O3 minus.
Yep, the 8 ending tells us it's probably going to come out of the box. So aluminum is Al, and it has a plus 3 charge. And nitrate is NO3 with a minus 1 charge. Now, do the plus 3 and the minus 1 fit together?
No.
They don't. We could, or we could do our crisscross, right? However way you want to get to your final product is fine with me. But we're going to take away our pluses and minuses, bring down the 1, and bring down the 3. So here's what has to happen. I'm going to show you this for this problem. Al needs a 1. So do I have to write the 1? No. But I'm going to need 3 of these NO3 atoms. So I have to put NO3 in parentheses to be able to add a 3 on the outside there. Okay, to signify that I need 3 nitrates, I have to add parentheses, right? Otherwise, it would look like this, AlNO33. Right, that doesn't work. So I have to make sure that I put those in parentheses, nitrate, and then I need 3 of those, and it goes on the outside. Okay? Can we reduce these 2 3s right here? We cannot because that's right. This 3 is part of nitrate's identity. It's not changeable. We're not going to change that one ever. Okay? Feeling okay? All right, let's keep trying. Let's try calcium sulfate. Calcium sulfate.
Sulfate is 4 minus 2.
SO4 minus 2.
And calcium.
And what is calcium?
Calcium is plus 2.
Plus 2. So what do we see about these 2 particular atoms?
They cancel out.
They're going to cancel. They're going to go together right away, aren't they?
Yeah,
So it just becomes CaSO4. Let's say that we had kind of made a mistake here and not noticed that they fit together. And what if we did our crisscross? We bring down the 2 and bring down the 2. That would be Ca2SO4 2. And so then we would look here and say those ones need to reduce down. Okay, and it just still ends up being CaSO4. Have you figured out what's the pattern for when I need to use the parentheses?
When you have double.
When there is a number at the bottom. When I need more than 1 of my polyatomic ion, I have to use parentheses. Right? Here, I only need 1 SO4 molecule to cancel out my calcium. So I don't use parentheses. But up here, I needed 3 of my nitrates to cancel out aluminum. So I have to use parentheses. Right? Anytime I need more than 1 of a polyatomic ion, that's the rule. Okay? Let's try barium hydroxide.
Barium. What is this?
Barium is Ba. It's in group 2.
Plus 2.
Okay, it's a plus 2.
Oxide is OH.
Ba is plus 2. Hydroxide is going to come from the box.
OH.
OH
minus one.
minus 1.
We can add one more OH
Right.
minus 1 to cancel.
Yep.
it out.
Yep.
Or we're gonna do the crisscross.
That's
link
right.
as well.
That's right. Either method works fine. So that would leave me with BA. And then can I just do this? OH2?
Yeah.
Yes.
Yes.
What's the difference, right? I have to have parentheses because if I leave it like this, that tells me I need 2 hydrogens,
No.
but only 1
Rocket.
oxygen.
But oxide doesn't have.
What the bracket
I don't
But-
see a number under it.
I know, but hydroxide is OH. That's its identity. And so if I need 2 of these OHs, I have to put this in parentheses. Because otherwise, all I'm saying is that I need 2 hydrogens, but I only need 1 oxygen. And that's not true, right? I need 2 hydroxides or OHs as a whole.
That's small.
Okay, try this one on your own. Write it out with its charge, then see if we need to crisscross. GA2
Rocket.
S.
3. Rocket. 3.
Agreed. Is that what we had?
That's small.
Right? Because gallium was +3 and sulfite was SO3 -2. So we do our crisscross and that's what we get.
What did it do?